So on Tuesday in lab, we reviewed acids and bases, the strength of acids and bases, and you learned how to make buffers. In lecture, we talked about how we can use an equilibrium constant to calculate the equilibrium concentrations of reactants and products. So, just as a review, let's do question 1. 1 mole each of H2 and I2 are placed in a 1 liter box at 490 degrees. What are the concentrations of reactants and products at equilibrium? So there's the reaction, and there is the equilibrium constant at 490 degrees. And I've also described the method you can use. So you want to balance the chemical equation, which is done already. You want to set up the initial amount, the amount that reacts, the amount at equilibrium. So that's just like doing a stoichiometry problem. You want to plug in the equilibrium amounts into your equilibrium constant expression. Then you want to solve for x, or whatever your favorite variable is. So what I'd like you to do is to set up this problem, and we'll see how the math looks when we set up, when we get to this point here, before we solve for x. Because like we discussed on Tuesday, we use math as a tool, and we don't want to overcomplicate things like solving polynomial equations or that's the only math term I know. Okay, so while you're doing that, I'm going to say that so far we've covered chapter 15, which is the chapter on chemical equilibrium. Okay, so question 1 has to do with chemical equilibrium and equilibrium constant, and calculating equilibrium concentrations. And then chapter 16 is the chapter on acid-base equilibrium. And we were looking at acid-base equilibrium when we were making buffers in lab on Tuesday. Okay, so on the board, we have the balanced chemical equation. We've set up the initial amount that reacts and amount of equilibrium. So for our initial amount of H2, what should we put in here? Okay, 1, now here. 1. And what out here? 0. Okay. And on the second line, the amount that reacts, X, okay. And here is going to be, and what out here? Why is it 2x? Yeah, so note that we want to look at the coefficients on a balanced chemical equation and figure out the ratio of H2, I2, and HI. And then at equilibrium, how much of each substance is present? Okay, so we have 1 minus x. And then here we have 2x. Okay, so now we can set up our equilibrium constant expression. So K, which equals 45.9. Now that's going to equal, let's see, HI squared divided by H2 times I2. So now we'll plug in our equilibrium concentrations into this equation. So for HI, that's going to be 2x squared. And then for H2, that's going to be 1 minus x. And for I2, it's going to be 1 minus x. And all that's going to equal 45.9. And it looks like we have some sort of quadratic equation to solve. You look very, very excited to solve a quadratic equation this morning. Now, can we assume that x equals 0 like we did in lab on Tuesday?
No.
Why not? Yeah, because this is a big number, so we can't make that assumption. So we actually have to use that quadratic equation to solve for x. And let's save that for another year. I mean, another time. Really, this is the part here. So you set up the equation, now you solve for x. Once you solve for x, then you can figure out the equilibrium concentrations. Okay, so we'll do that another time. So we were looking at acids and bases, so let's take a look at question 2. 0.1 molar hydrochloric acid, which is a strong acid, has a pH of 1. So why does 0.1 molar HCl have a pH of 1? Yeah, so based on that formula, pH is equal to the negative log of, so pH is equal to the minus log of H plus. Now, do you know what the H plus concentration is based on what you're given? Because it says you're given 0.1 mole HCl. So based on the concentration of HCl, how do you know the concentration of H plus? Okay, so if we have HCl, this will dissociate into H plus and Cl minus. So we can do the same thing as we did before, just in case of the amount that reacts, amount of equilibrium. Okay, so this is 0.1 molar, and this is 0 and 0. How much of the HCl reacts? Well, we know that X equals a number. Yeah, because we can say it's X the way we said it before, but we know what X is going to be. Yeah, X is going to be 0.1. And we know that X, the amount of HCl that reacts is 0.1 because... Yeah, because we know all of HCl is going to react because HCl is a strong acid. Okay, so as a strong acid, this dissociates completely into its solute. with ions, so this is going to be 0.1, which means that how much H plus react or is produced? We get 0.1. How much Cl minus is produced? We get 0.1. So how much of HCl is at equilibrium or is left over? So 0. And then for this one, and then for that one. Okay, so all we got to do is plug in that number there and we should get a pH point. Okay, so let's go on to part B. 0.1 molar acetic acid is a weak acid. It has a pH greater than 1. Calculate the pH of 0.1 molar acetic acid. And we did this calculation on Tuesday in lab. And what was the answer? Was the pH 1, 2.9, or 7? Yeah, so the answer was 2.9. Okay, so again, just as a review, to do that calculation, how do you do that again? Yeah, so we have to look up the Ka of acetic acid, so let's just do that one more time. Okay, so we have acetic acid. And this dissociates into H plus, and what's the other ion? Yeah, CH3, COO minus. We can look up Ka in table 16.3 in the textbook. And Ka for acetic acid is equal to 1.8 times 10 to the minus 5. Then we'll just do the same thing. So we have the initial amount, the amount that reacts, the amount at equilibrium. So for the initial concentration of acetic acid, that's equal to 0.1, and that's 0. So we know how to fill in the blanks now. Tell me when you get tired of watching me do this, then I know you know how to do it, and I won't have to do it anymore. Okay. And then we plug it into this equation. And in this case, can we assume that x in the denominator is equal to 0? Yeah. And we can do this because we've got a very small Ka value. So this tells us that the extent of this equilibrium reaction is very, very small. In other words, not much of the acetic acid is going to be associated with ions. Okay, so that's going to equal 0. This simplifies the equation. We solve for x. And when we solve for that x, that's equal to the H plus concentration, which is also equal to the Cl minus concentration. Then from here we can calculate the pH. Okay, so I think we've done this calculation 3 times, and someone was telling me that to learn something, you got to do it 7 times. So we have to do this 4 more times. Okay, so let's go on the next slide. So we know that this is a review from Tuesday. Water behaves like an acid or base. Why does water have a pH of 7? And how do we know what the H plus and OH minus concentration is in water? So to figure that out, I put it in small print here. We got to do another equilibrium concentration based on this chemical equation and based on Kw. So based on this chemical equation, the Kw, we can do another equilibrium calculation. And should we do that equilibrium calculation? This will be equilibrium calculation number 4. If we do, which means we have to do just 3 more. Or you just skip it. I think we just skip it. But we have some other ones to do anyway. Yes, we do an equilibrium calculation. We do the same thing we did here. Instead, we have a different equilibrium constant. We solve for x equals H plus, calculate pH. pH of water equals 7. So if the pH of water is 7, that means only one water molecule in 10 million dissociates into H plus and OH minus. So it's only 1 in 10 million that does anything. Then we also talked about why when in pH 7 that's considered neutral, and it's considered neutral because so the concentration of H plus equals concentration of OH minus. Then we also looked at POH. So POH is defined as minus log of the OH minus. So what is the POH of water?
7.
Yeah, so it's equal to 7. So if the pH equals 7, the POH also equals 7, and we know that from this equation, pH plus POH equals 14. And we also talked about every acid having a partner or conjugate base. So just like you have a lab